During the past year, the federal government updated guidance on conducting benefit cost analysis, especially pertinent to decarbonization investments. And there's two documents that Brian will be talking about today. One is Circular A4 from the White House, and another is the updated social cost of greenhouse gases that were released in November and December of this past year. Thus, policymakers and companies in Louisiana utilizing federal incentives are being asked to credibly document these emissions reductions and conduct these benefit cost analyses on these projects. Louisiana, in addition, we've got federal offshore leasing, obtaining LNG export permits, as well as methane regulations. And these companies impacted by these also have a vested interest in understanding these federal guidelines and whether these proposed policies pass the litmus test that, of course, was given by the federal government. So we're happy, therefore, today to have Dr. Brian Prest come and give a talk entitled Valuing the Cost of Climate Change, the Social Cost of Carbon. Brian is the director of the Social Cost of Carbon Initiative at Resources for the Future, located in Washington, D.C., or RFF. He's an economist and fellow at RFF, specializing in the economics of climate change, energy economics, and oil and gas supply. Brian has a Ph.D. in environmental science, environmental and resource economics from Duke University. So in September of 2022, Brian was a co-author on a paper published in the journal Nature entitled Comprehensive Evidence Implies a Higher Social Cost of CO2. That was one of the three works that was cited in updating the social cost of carbon number from about $50 a ton to about $190 a ton, which has had enormous implications for cost-benefit analysis of these federal programs. So without further ado, we give Brian a warm welcome and thank you for coming to LSU.
Thanks, Greg. Yeah, thanks for having me here. As Greg said, I'm a fellow at Resources for the Future. If you're not familiar with RFF, we're a nonpartisan think tank research institution based in Washington, D.C., and our goal is to inform environmental and natural resource decisions. This is going to be the first time I've given the talk in this form, and so forgive me if I may be a little stilted. I'm still trying to warm up to this. I'm giving this very similar lecture to my class at Georgetown on Monday, so you guys are the guinea pigs. Welcome to any feedback. So we're talking about valuing the cost of climate change using the social cost of carbon. I'm also going to talk more generally about benefit cost analysis, how it's used both by the federal government and, as Greg said, in other contexts as well that I'm learning about down here in Louisiana. But just kind of as scene setting, this is a very blurry photo I took last night out the window of my Uber as I was coming from the Baton Rouge airport. You can't really appreciate it from this photo, but this was a pretty large flare coming from the Exxon facility off of the highway. And it's the only really reason I could see it last night. And I saw this tweet about them noting this. I found a better photo online, so let's just pretend that my photo looks like this one. So I don't know exactly what they're. Do you think this is gas, Greg? Is this, or is this something? Yeah, just gas. Okay. So so when they're flaring this, they're turning methane, which is itself a potent greenhouse gas, into CO2. And so how do we think about valuing the costs to society in monetary terms of the emissions that are created by any type of combustion resulting in CO2 in the atmosphere? How do we think about valuing the costs of methane? That's probably not a perfectly efficient flare right there. And so there's also some methane being escaped. What is the dollar value cost of that? We often think about this in context of regulations. Perhaps it may be relatively easier to quantify the costs of a regulation or any other policy that's going to reduce emissions. How do we think about, well, what are the benefits of that? Do the benefits justify the costs? And if not, how can we improve policies to achieve net benefits? So that's where the social cost of carbon comes in. You can't see the text, but the social cost of carbon, you can't see all the text, but the social cost of carbon, just to level set, is also sometimes called the social cost of carbon dioxide, because it's really about valuing the CO2, is an estimate in dollars per ton of CO2 of the economic costs, or sometimes called damages, of an incremental ton of CO2 emissions. So when I say incremental, I mean one more, not valuing the total damages of all emissions on the climate. What is that incremental, or in calculus terms, marginal ton of CO2 emissions? And this is meant to reflect not just the cost today, but the fact that CO2 has a warming effect for hundreds of years out into the future. And so in some sense, it's on reasonable timeframes, it's an irreversible impact. How do we think about that stream of impacts out into the future and convert that into a present value dollar per ton metric? The SEC has long roots in the economic literature. It kind of has its roots in part into like Pigou writing in the early 1900s about externalities and how do we think about internalizing externalities to internalize social costs and achieve efficient outcomes. It has its more practical roots to Bill Nordhaus writing in the 1970s and 80s on valuing the global commons. I think the original paper was how much should we graze the global commons, and thinking about treating the atmosphere as a common pool resource that we need to value. Typically has the most common use for the social cost of carbon is for policy analysis, in particular regulatory impact analysis about benefits and costs, as I alluded to. But it's also often seen as a benchmark to a carbon price. Economic theory says that an efficient way to internalize the externality that is carbon emissions is to price it. And the optimal price from economic theory should be equal to the marginal damages associated with the pollution. And so that's where the idea of an incremental ton of CO2 and valuing that incremental ton of CO2 comes in. Now, as Greg mentioned, the US EPA recently finalized an updated estimate of $190 per ton of CO2, which is a nearly fourfold increase from the previous estimate of about $50 per ton. And this is based on coupled climate economy models that I'll go into more detail later. But as Greg mentioned, this is a very substantial increase, and this $190 per ton of CO2 number is quite large, and so has very big implications for understanding the benefits and net benefits of various different kind of climate policies. So in this talk, just to give you an overview, I'm going to start with the basics, the basic economics of Pigovian taxes and benefit cost analysis, go through some examples of how it's used, how the social cost of carbon and also the social cost of methane as well is used, and then go into, well, how do we actually arrive at this estimate of the SEC? It seems like a very ambitious undertaking to value all the impacts that an incremental ton of CO2 or methane emissions has on society in dollar terms. So this is kind of your Econ 101 the totem, sometimes people call it, of your supply and demand curves. So we typically think of demand curve representing the marginal benefit to consumers of some goods. You can think of on the x-axis is oil or apples, and so the first apple we consume is worth more to us than the fourth or fifth apple we consume in a single sitting. And so the demand curve reflects the marginal benefits of consumption of a good, and it slopes downward. Supply curve, by contrast, it reflects decreasing returns to scale as we ramp up production and say for a given amount of a capital stock. And so the marginal cost curve is the supply curve. And in standard kind of Econ 101 competitive market story, they form to create an equilibrium price and quantity at their intersection. And a standard result is that the competitive outcome in this kind of stylized simple market is an efficient one. The idea is, wrong button, is that this competitive outcome can maximize what we call social welfare or total surplus to society from the consumption and production of that good. We represent what's called consumer surplus, which is basically the benefit, that's the area below the green line, but above that price. So it's the benefit to consumers less the price that they had to pay to get it. And by contrast, the producer surplus is the revenue that the producers get minus the costs that they have to incur to produce the good. And this is the outcome that maximizes surplus because we're at a place where marginal benefits are equal to marginal costs. If we were producing less than that, then there would be essentially gains from expanding output, gains from trade, because the marginal benefits exceed the marginal costs at that point. And so generally speaking, the net benefits to society is this blue triangle, which is equal to the total benefits of the entire area below the green line minus the costs of production, which is given by the red area. So, wrong button. that's what I just said. So here, in this case, the social welfare, the surplus to all members of society is maximized by the competitive outcome, or sometimes called an economically efficient outcome, which is an outcome that maximizes total surplus or total welfare. So this is great. Competitive markets can maximize social surplus, but we know that markets are not always perfect. There are things called market failures. There's many different examples. So some examples here include information asymmetries, when there's market power, like a monopolist or oligopoly, when there's public goods. So the benefits of the production of some goods, a common example is like a park or a fireworks display, are broadly distributed and what's called non-rival. So my consumption of that park doesn't hinder yours. And then finally, the one I'm going to focus on in this talk is externalities. This is the carbon emissions are kind of the classic example of an externality. So in the previous version of the previous supply-demand graph, we showed that total surplus is maximized in this competitive equilibrium, but with an externality that changes things. An externality is a case where someone's private action, say the combustion of a gallon of gasoline that reduces CO2 in the atmosphere, has an unintended effect on a third party that's not party to either side of that transaction. This changes the story. And the kind of classic example, a classic economic approach to addressing externalities is what's called a Pigovian tax. So we put a value on that marginal damage associated with that, say, negative externality. We price it. That essentially takes that cost that was being offloaded onto someone else and internalizes it. And it gives an incentive for the relevant parties to account for that cost in their production and consumption decisions. The way this is operationalized in our kind of standard supply-demand graph is that, well, the red line was previously the marginal cost of production. Now we're saying, well, there's actually an additional cost to society of producing that good or consuming that good that's not represented in the private costs. And so because producers or consumers don't have to pay that, they don't act to conserve that good or to mitigate those damages. And so now the marginal social costs are higher by the amount of the externality. And so the equilibrium is actually producing more of the good or more of the pollution, more of the externality than we would normally want. We'd ideally want to be at the red dot, but instead we're at the competitive market case, we're at the blue dot. And the damages are given by this brownish triangular area, which is basically just reflecting the areas where the total social cost of producing that good are higher than the benefits given by the green line of consuming that good. So I would normally walk you through all of the math here, but I'm not going to subject you to that. But if you do the math, you basically find that in the competitive equilibrium case, the total social welfare is given by the A letters, but minus the damage to the right of that socially optimal level. When we impose a Pigovian tax on the supplier, or we could do it on the demand side too, you get the same outcome. You have social welfare that's A instead of A minus C. And so what's called the deadweight loss of the over exploitation of, say, the negative externality is given by the C. So I will walk through my students, through this on Monday, but for the purposes of this, I'm going to move along here. So the question is, how do we think about valuing both the costs and the value of the externality? That's the wedge between the brown and the areas. And so this comes up commonly in benefit cost analysis. So the basic framework for a benefit cost analysis is to take a policy or a change in policy, and we evaluate its net benefits by comparing its benefits compared to its costs, benefits minus costs. And if the benefits are greater than the costs, then we say the policy has positive net benefits to society. At the federal level, this has been done for more than 30 years now. In fact, was done before that, but it was required by Executive Order 12866, which was issued in 1993, which requires a regulatory impact analysis, a benefit cost analysis for all major regulations, which basically means more than $200 million in annual economic impact. And this executive order has withstood one, two, three, four, five administrations. And so there's bipartisan support for conducting benefit cost analysis. Why is it relevant? Well, poorly done regulatory impact analyses or poorly done benefit cost analyses, BCAs, can make regulations vulnerable in the courts because if they are indicating that an agency, for example, is acting, the term of art is arbitrary and capricious actions, then it violates the Administrative Procedure Act of 1945. And so BCAs are important to making sure, one, that we're actually making good policy, but also to make sure that rules are not just constantly being overturned and changed. So the question when it comes to climate change is how do we measure the benefits of costs in the context of climate change? And this seems hard. You know, we might think about a regulation on power plants or fuel economy for vehicles being relatively straightforward, maybe not always straightforward, but probably easier to quantify the economic costs associated with, say, installing certain kinds of technologies, whether it's scrubber or something like that. But how do we put a dollar value on benefits? And this is not just an issue in climate change; it's also in conventional air pollutants. How do we put a value on certain kinds of, say, conservation or saving certain kinds of species? That tends to be a lot harder. And so there's a vast environmental economics literature that tries to get at this. So there's a lot of bullets on this slide. These are kind of the key issues that we think about when we're conducting benefit cost analysis. So this is a really basic one. This is the kind of with and without principle. But we want to do a real comparison between what would the world look like with this policy and what would it look like without this policy holding everything constant. In the kind of litigation space, this is often comparing what's called the real world with the but-for world. And so what would the world look like but for some particular action or intervention? That's pretty kind of obvious. A more sticky issue can be standing. Whose costs and benefits count when we're thinking about conducting, assessing benefits and costs? Climate, this gets particularly controversial in climate because there's a question about should we count all the impacts of carbon dioxide emissions around the world, or should we just be thinking about the impacts occurring to the jurisdiction that's considering a policy, whether it's the US? Should the US consider only US benefits? Should a state consider only state benefits? And so standing is not always so obvious. There's an issue around something called co-benefits. So let's say we're imposing a regulation that is primarily meant to reduce CO2 emissions, but it also reduces particulate emissions that has impacts on human mortality. Should we be thinking about co-benefits? And I think the economics community has a consensus that we should, because any benefit of a policy is a benefit. But there have been some disagreements about that, especially in cases where the co-benefits could be much, much larger than the direct benefits of a policy. Then there's a question about monetizable and non-monetizable benefits. There may be real benefits to society, but we just can't put them in dollar terms. Think about subsistence fishing. There's no real necessarily a market for that, but so it might be hard to put a dollar value on. But there's of course a benefit of that. Distributional effects. Does this disproportionately fall on poor or disadvantaged communities, both on the benefits and the cost side, because those could be different either way. And then comparing costs and benefits occurring at very different points in time. This is where the term discounting, net present value comes into play. And this I've also put in green, just like for the domestic versus global comparison, because in many cases, the costs of an investment or a regulation tend to be upfront investment costs, say installing a technology, whereas the benefits occur gradually out into the future. This is especially the case in climate change, where, as I said earlier, the emissions of CO2 last very long into the atmosphere. And so thinking about valuing those future impacts happening many decades or even centuries out into the future in today's terms. And this one, I just want to make sure include primarily for my students that from a social welfare or economic perspective, it's often argued that the benefits of some type of policy or investment is jobs created. When we think about this from an economics perspective, we think of jobs as a labor cost, as an input cost. So I just want to be very clear that when you're tallying costs and benefits, you should not be putting jobs in the benefit category. If anything, they fall in the cost category. And maybe the perhaps intuition behind this is that if you can imagine two worlds that have the same amount of wealth, but in one world, you have to have an additional 1,000 people working to produce that wealth, that's obviously a worse off world. So the key themes I'm going to come back to for climate change are the ones in green here, discounting and the standing domestic versus global. So here's an example. The text is a little bit hidden, but this is I'm going to go through an example of how costs and benefits are often calculated and compared in standard regulatory impact analyses done by the federal government and elsewhere. This example is the recent EPA methane regulations on the oil and gas sector, so something that may be familiar to a fair number of folks in this room. These were finalized just in December. So the picture on the left is showing that methane can often leak from oil and gas infrastructure, but you can't necessarily see it with the naked eye. So this looks like, I don't know, it could be a big event. I'm not entirely sure, but it looks pretty big. And so, as I said, they finalized these regulations in December with the goal of preventing 1.5 billion metric tons of greenhouse gas emissions. I guess that's probably in CO2 equivalent, and deliver billions of dollars in health and economic benefits. But how do we come up with this estimate, the billions of dollars of health and economic benefits? That's where climate and environmental economics come into play. So I don't really need to pitch this to the folks down here. So methane can often leak from oil and gas infrastructure, and it can be hard to see, but some aerial imagery can pick these plumes up. And the regulations have a number of components. So there's monitoring requirements. So every so often, with the frequency that varies with the kind of infrastructure or well site, you have to go, oil company will have to go monitor its infrastructure for leaks. Technology requirements like using certain kinds of zero emission pumps and controllers and so on. Limits on routine flaring. There's a new super emitter leak detection and repair program that basically says if someone detects that there's a big leak, they'll report it to EPA, and EPA will notify the company who has to go fix it within a certain amount of time. And lots more in here that some of you might even know a lot better than I do. And also sitting in the background here is a completely separate but also important policy that was implemented as part of the IRA, which is basically the only stick in a policy or a law that's mostly carrots. And this is a fee on methane emissions from the oil and gas infrastructure. And this is tied closely to recent but past estimates of the social cost of methane. So just as another kind of example. So again, so there's this fact sheet that's saying, you know, we're going to have this this policy is going to reduce methane emissions, and it estimates the net benefits to be nearly $100 billion in present value of benefits, or equivalently something in the order of $7 to $8 billion of annualized benefits. So where does this number come from? So this is, dives into the regulatory impact analysis done by EPA for this. Don't worry about all the columns. I just want you to focus on this first column. And this is putting a price tag of on the climate benefits of this regulation in present value at $110 billion a year. All the numbers are in millions, so the 110,000 is $110 billion a year. They also estimate ozone health benefits from VOC, volatile organic compound reductions on the order of it's not 110 billion a year, it's 110 billion present value. 7 billion present value for ozone health benefits. They compare that to the net compliance cost of 19 billion, which in turn represents the direct compliance cost of 31 billion, minus the fact that if they're capturing methane, methane is the primary component to natural gas. There's value of that product, although although it falls short of the cost of capturing it. And so the net compliance cost is the delta between these two. So that's your 19 billion. And so that's where your net benefits comes from. It's the 110 plus the 7 minus the 19. And so where does the 110 come from? Well, down here, you see that they're estimating that this rule will reduce something on the order of 50 8 million short tons of methane over the 15-year life of the program. And it's a little bit more complicated than this, but the back of the envelope gets to it. The recent updated social cost of methane number is $1,900 per ton of methane. So you can just do the arithmetic, 58 million times 1,900, and that gets you your 110 billion up front. So the math is pretty simple. Like if you have the number, if you have this $1,900 number, you basically just can multiply it by the tons reduced. There's some nuances in that this is going to vary over time. Like the dollar per ton number will vary over time. The number of tons will vary over time. So you'll have two things that are varying over time, but each year you just multiply them together, and the calculation is fairly straightforward. But where does this come from is the focus of a lot of the rest of this. So more generally, how do we think about estimating environmental benefits? How do we value the environment? Well, as economists, we start from the premise that we shouldn't be paternalistically imposing, our view of what the value of the environment is. We should look at people's preferences, how much they value the environment, and that should be reflected in our quantification of the benefits of environmental protection or reducing emissions. And so how do you think about valuing something like this? This is from the Exxon Valdez spill. It can be hard, but there's multiple different approaches that have been developed by economists. A standard approach is what economists like is called revealed preference. So we look at observed consumer behavior and to see, is there a way we can figure out something about observed behavior or observed market prices that could infer some value here. That's obviously going to be hard for this kind of case because there's not really a market for cleaning oil off of birds, although there might be some observed preference from people's donations to certain charitable causes. The kind of key ones that we like in revealed preference are what's called, one is a hedonic approach, where we look at characteristics of goods and services that people do buy that may reflect some preference for environmental amenities. So a classic example is a house that's closer to the beach will typically be valued more. People will be willing to pay more for a house that's close to the beach than one that's further away. So you can infer something from that about the value of being nice views of a nice beautiful beach. And you can also think about, well, what happens if there's an oil spill? How does that change that? Another example of a revealed preference approach is averting behavior. So we can see, people spend money on things that reduce their risk. And how does that tell you about, say, the value of clean air? Well, if people spend a lot more on air filters when air quality is worse, that tells you something about their valuation of clean air in terms of, protecting their own health. If there's a water contamination, then you can see that people spend more on bottled water. What can you learn from that? You can infer something. In all these cases, we can think about quantitatively using data on prices and expenses in context of these kind of environmental threats to infer something about this. There's also a method called travel cost approaches that look at how much people are willing to spend to visit, say, a recreational fishery or a national park. And how does that vary when, say, the price of the travel goes up and down, say, because of the price of gasoline? Again, we can infer something about people's willingness to pay based on their observed behavior and interaction with environmental amenities or related products. For something like the birds case, we often have to rely, we can't necessarily infer something from market behavior, so we often have to use something called stated preference, which are either surveys where we essentially ask people how much their willingness to pay. These suffer from the concern that talk can be cheap, and so people might overstate their willingness to pay, and so there are attempts to deal with that. And you can also ask people to do choice experiments. Would you be willing to pay this much for this much environmental improvement on some specific metric? Now, these are mostly for conventional environmental goods, and these are often also quite hard to do with climate change, although some people have tried. And so what's more common in the climate space is the use of something called an integrated assessment models. There's a whole suite of these. These are coupled models of the climate and the economy that try to pair those things together to see how does a change in climate affect society in monetary terms. And so that's what we'll be talking about primarily for the rest of this talk. And I just want to pause because something that's really relevant to the case of climate change is how do we put a value on a human life? A very large component of climate damages are increased human mortality risk due to the offsetting effects of very hot days. More people die on hot days, and a reduction in mortality on very cold days. Fewer people die on very cold days. So as we shift that distribution of temperature to the right, what is the net impact on human mortality? Well, we can think about using epidemiological modeling to try to put an estimate on the number of additional deaths. But how do we turn that into a monetized value? And so the standard approach here is to use something called the value of risk reduction, specifically for mortality risk. Sometimes this is also referred to as the potentially misleading term, the value of a statistical life. And this sounds kind of like the value of a life, but it's not the value of a life. It's the value of a reduction in the risk of mortality. Now, even if it were the value of a life in monetary terms, basically how much someone would be willing to pay to reduce their risk, we tend to not think that it should be valued infinitely. If we value every reduction in mortality risk at an infinite number, then we would essentially not be allowed to leave the house. We'd have stoplights on every corner. The fact that we don't have that tells us that we as a society are willing to endorse some type of increased mortality risk in exchange for other benefits. So how do we put a number on this? So the EPA estimate is, roughly speaking, $10 million per statistical life. This is basically saying that the best estimates suggest that if someone is willing to pay $100 a year to reduce their mortality risk by a 1 in 100,000, again, over that course of that year, sorry, 100,000 risk over that course of that year, well, then the product of those two things is the value of a statistical life. There's a description from EPA's website that lays it out. It says, suppose each person in a sample of 100,000 people were asked how much he or she would be willing to pay to reduce for a reduction in their individual risk of dying of 1 in 100,000 or 0.001% over the next year. Now, suppose that the average response to this hypothetical is $100. Then the total amount that the group as a whole would be willing to pay to save one statistical life, so 1 in 100,000 over times 100,000 people, is 100 times 100,000 people, or 10 million. And this is what's meant by the value of a statistical life. Importantly, is not an estimate how much money any single individual or group would be willing to pay to prevent the certain death of any particular person. And so this is core to the valuation of any type of environmental policy, climate or not, that affects mortality risk. This number doesn't come from survey evidence. This number comes from a literature on that's largely based on revealed preference using evidence from labor markets. The idea is that if you can statistically control for the differences between jobs, and just hypothetically, suppose you see two jobs, and one has a higher accident risk, but it also pays more, because otherwise, if the jobs are identical, otherwise they would have to pay more to induce a worker to take on that additional accident risk. Then you can use statistical methods to essentially infer this number, and that's where this $10 million comes from. So this is kind of important to a lot of valuation, which is why I wanted to spend a whole slide on it, and it's also used as part of the social carbon modeling. I mentioned previously, switching gears, that that discounting is also a key component of valuing climate impacts into the future. For anyone with a finance background, this is hopefully a straightforward idea, but the idea about discounting is how do we value impacts in the future? When we typically think that $1 or any impact received in the future is worth less than the same dollar received today. There's multiple conceptual reasons for this, but the kind of simplest and most intuitive one is the fact that you can earn interest on savings. So suppose you can earn, you have a risk-free savings account with say a real interest rate of 2%, which is about where we are today. If you received $1 today and you put it in the bank, then you'd have $1.02 in the future. Just 1 times 1 plus R. For the exact same reason, a dollar received next year is worth less than a dollar today, just divided by 1 plus R. And so a dollar received in the future is worth about 2% less of 98 cents today. More generally, we have this present value formula, which should be familiar from finance, which says that the future value received in some period t, there should probably be a subscript t there, can be discounted to a present value just by dividing by 1 plus R to the power of the number of years into the future. And this can matter a lot, in particular in context of climate change. Why? This is a graph showing how 1 additional gigaton carbon released into the atmosphere today, how much that is going to increase global surface temperatures over time. So over just a modest number of years, it ramps up, and it's basically flat for more than 300 years. This is because carbon has a long residence time in the atmosphere. Its warming effects are felt for centuries out into the future. For most conventional air pollutants, this basically comes back down to zero immediately, and so discounting is not as big of a deal. But in the case of carbon dioxide, then how you think about what is this irreversible effect going to have in the distant future, so 100 or 200 years from now, how much do we value the impact to that future society today? So just as a kind of quantitative example, let's look at the year 2100. Suppose we have this increase in global mean surface temperature in 2100, and suppose we put we say each dollar of impact that in that year, how much is it worth from a present value perspective, from today's perspective? So that's the same formula from before. It's just 1 over 1 plus R to the power of 76. That's the number of years between 2024 and 2100. Here's 3 different candidate discount rates. So if we use a 2% discount rate, consistent with today's real interest rates, that's $1 in the future is worth 22 cents today. If we just increase the discount rate by a little bit, or 2% to 3%, it's now worth 10 cents, which is half as much as under a 2% discount rate. And this is due to the power of compounding in discounting. If we use a 7% discount rate, then it's worth 1/38 times as much under 2%, or sorry, under 7% versus 2%. And so seemingly modest changes in the discount rate can lead to multifold changes in the present value of any impact. As Greg mentioned, there were some recent updates to a document called Circular A4. Circular A4 is issued by the Office of Management and Budget, which reports to the White House. And the last time A4 was updated, it was 2003, and the A4 offers benefit cost guidance to all agencies on a number of different dimensions, including some of the things I already talked about in terms of say standing and other things. But a key piece is its recommendation on the discount rates. What it did previously in 2003, so right around here, is it looked back 30 years. It took an average of real returns on government debt. It came to an estimate of 3%. And then it had a separate argument for the 7% discount rate that I showed you in the previous slide. That is very technical, and I'm not going to have time to go into here. But basically, for the 3% number, they in 2023, they took the same calculation they did starting in 2003, the 30 years up to 2003, so 73 to 2003, and they updated that analysis with almost no changes to go from 1993 to 2023. And you can see that we've had much lower interest rates over the past several decades. And when you do that updated average, you get an estimate that's pretty close to 2%. And so, as I showed on the previous slide, this can have a big impact on the valuation of things that happen far into the future. So, such as a factor of 2 for 2010, this difference would be even bigger for 2150 and so on. And so this means that modeling the long-run implications of the kind of irreversible impacts of carbon emissions is quite important to putting a value on it. So more generally, the update to Circular A4 also discussed the regional focus. This relates to standing. Who counts? Is it just impacts within the United States of climate change, or is it impacts more broadly? So the old A4 was focused on these two discount rates of 3% and 7%. There was focused primarily, but not exclusively, on just domestic scope of impacts. And then the updated version focuses more on this 2% discount rate. And then it has a much broader discussion of saying, well, when you have international negotiations or you over a pollutant, or there's a global externality, which perfectly describes climate change, then they leave some room open for not just having a domestic scope of analysis, but a global scope. So this will be key for the estimates. And just to give you an example, this is the previous estimates of the social cost of carbon. The central one is $44. It's the same as the $50 one, just in a different, it's in $2011 instead of $2020. Was so around $40 to $50. That's at a 3% discount rate, global scope of analysis. And you see if you either switch to a 7% discount rate, global, or you keep the 3%, but you go domestic, it has a big impact on the social cost of carbon. And if you do both, it can quickly go from 44 to essentially 1. And so that makes these two questions about discounting and scope of analysis really key. Okay, that's kind of the background to benefit cost analysis with some teasers about what are the key factors. Now I'm going to dive into some recent updates, including work by myself and our folks at RFF and our partners at various other universities and EPA, as well as diving into a very new paper just published a couple of weeks ago by Bill Nordhaus, again, a Nobel Prize winner, who recently updated his estimate of the social cost of carbon. So I've already talked you through the kind of definition of it and the recent updates. News article on this. Let me just move on. And I want to talk a little bit more about, so these numbers, as I said, on the previous slide, $190 per ton of CO2, how are they typically used beyond just benefit cost analysis? So a common, as I already mentioned, the Pagovian tax is the kind of standard economic remedy to an externality. And so a Pagovian tax should be based on the marginal damages associated with the incremental amount of pollution. And so as a result, it's kind of standard basic result from economic theory that the common benchmark for a Pagovian tax is based on the social cost of carbon. And this can be used whether you're thinking about a carbon tax itself or what would be an efficient, economically efficient market price for emissions allowances under a cap and trade program. Importantly, I mentioned the methane fee earlier. The methane fee written into IRA is $1,500 per ton of CH4. It ramps up from $900 to $1,500 over 3 years. And that very clearly has its roots in the previous interim estimate of the social cost of methane. Now, while the EPA update changed the social cost of methane a little bit from $1,500 to $1,600, technically, as written into the IRA, the fee remains pegged at this $1,500 value rather than explicitly tied to the social cost. So if we were to actually do this and to have a carbon price or a carbon tax based on this updated $190 a ton social cost of carbon estimate, what would be the impacts? As the title here says, it would be essentially a game changer for the relative total costs of different forms of energy. This is effectively the cost in cents per kilowatt hour of alternative sources of electricity, not accounting for any externalities such as the social cost of carbon or conventional air pollutants like particulates. And so gas, clear winner compared to all these others. The middle bar here, I should say, this is from Michael Greenstone's lecture, which was I highly recommend. It was the keynote lecture from the American Economic Association in January. Then what if we think about pricing not carbon, but particulates? So, the impacts on, conventional air pollution and their concomitant impacts on human mortality. Changes coal a bit, makes coal a bit more expensive. Gas still clearly the cheapest option. Now we throw in the social cost of carbon. That changes a lot. Now we have nuclear and solar and wind, even with the natural gas backup, so not having to worry about any intermittency effect, now those look a lot cheaper. So it completely changes the ballgame here. And so this matters a lot if we're thinking about what are the social costs of alternative different sources of electricity. This slide is just to point out that this matters a lot. We already talked a little bit about on the benefit cost side. So the other use of the SEC is quantifying the benefits in regulatory analyses. And as I already mentioned, this is required under Executive Order 12866. But actually beyond that, it's accounting for the social cost of carbon itself is actually required under court order dating back to 2007. Basically, what happened is the National Highway Transportation Safety Agency issued fuel economy standards for light duty vehicles that didn't account for the social cost of carbon anyway. It didn't put any dollar value on the benefits of reducing emissions. And the courts found that, as I mentioned earlier, this can make rules legally vulnerable. So the ruling said that NISTA's reasoning is arbitrary and capricious for several reasons. First, while the record shows that there is a range of SEC values, so there's uncertainty in what the SEC, the value of carbon emissions reduction is certainly not zero. And so not incorporating it at all is, the court reasoned, is no different than treating it as a certain value of zero. And so since then, the accounting for the SEC has been required in regulatory impact. We already touched on some of this stuff, that it can be relatively easy to account for the cost of a regulation, but it's harder to account for the benefits due to the global impacts. This comes back to the standing question, the long time horizons at play and the role of discounting. And also just more generally is that the impacts of kind of conventional air pollutants tend to be much more narrowly targeted. Like we're thinking about PM, we think, okay, that affects respiratory and cardiovascular health of people in the vicinity of where the pollution is occurring. But because there's so many different impacts of climate change and they happen not just near where the pollution comes out, but also all around the world, then accounting for the multitude of impacts just is a big challenge. So as I already mentioned, the EPA's update, the $190 a ton of CO2 is based on the combination of three recent models. So the first one is the GIVE model, and that's what I'm going to talk more about. This is the paper that Greg alluded to that we published in 2022 at Nature. Our central value from that paper, from the GIVE model, GIVE stands for Greenhouse Gas Impact Valuation Estimator. Our central value was $185 per ton of CO2. Then there was work done by Michael Greenstone's group at Chicago and elsewhere called the Climate Impact Lab. Their model is the data-driven social cost of carbon impact model, I believe, DSIM. Their central estimate was $190 a ton of CO2. And then there was a third source that they drew upon that had about $200. And then they took the simple average basically of these three sources to get their central estimate at EPA of $190 CO2. Because the GIVE model is our model, I'm going to give you more detail into that. But first, I just want to mention what's included in all of those numbers. So there's essentially 4 to 5 categories of climate impacts included. I mentioned there's a multitude of many different impacts of climate change. Not everything is represented. So those numbers represent the combination of temperature-driven mortality, both heat and cold-driven mortality, impacts of agricultural yields, impacts on heating and cooling expenditures, again, due to specifically heating and cooling buildings. So again, there's offsetting impacts. Russia is going to have less cooling expenditure in a warmer world. And so those are benefits to Russia, but also to other cold countries like Canada. So accounting for those offsetting impacts, offset, of course, with much higher cooling expenditures, particularly as less developed countries develop and get AC. Impacts on coastal infrastructure affected by sea level rise is included in this model. This is mostly flooding and inundation, not like storms or anything like that. That's not accounted for. And then impacts on labor productivity are also included. This is a table from the EPA report. Basically, any All the blue circles or blue half circles are things that are explicitly accounted for in the estimates. The half circles are partially accounted for, and then the open circles are impacts that are not yet accounted for in any of these numbers. So there's a bunch of different things that are just really hard to monetize, to put into dollar terms. And so there's ongoing work to try to account for. I'm going to skip over this, and I just want to talk about a bit about how we think about estimating the impacts of climate change. And this is from a nice paper from Tamara Carlton and Saul Sang in 2016 that predates a lot of the work I've been describing. And the idea is that how do we use empirical data to try to tease out how different social impacts are affected by climate change. So first of all, I want to make the point that weather and climate are different things. Climate is what you expect, weather is what you get. And so the top panel is saying here we have a distribution of a climate variable, say it's the daily high temperature or something like that in a particular location. Under a changing climate, you would expect both a shift in the distribution, so say warmer temperatures on average, but we also expect maybe a change in the spread of that distribution, so maybe more extremes. And so so as we move from climate 1 to climate 2, you get, say, more of these kind of high extreme outcomes in the climate variable. And how do we think about converting that into an impact on society? So what we often have something called like a dose response function, which is an empirically estimated function that says, for example, you could think about the y-axis here being human mortality as a function of temperature. And so, what we do see in the literature is that when we start at a cold temperature and it gets warmer, human mortality goes down. Less people die on really, when you have fewer really cold days. At the same time, when you have hot temperature and it gets hotter, then you have mortality increase. Further, human adaptation also suggests that relationship might actually be different under a different climate. People expect different weather patterns, and so they adapt in response. Maybe they're going from the climate 1 to climate 2, that some people who didn't have air conditioning in, say, Washington State before that big heat wave a few years ago get air conditioning, and that makes them less sensitive to the climate shocks. And so when we think about estimating the impacts on climate, we need to think about both the changing in the distribution of, say, weather outcomes, as well as the change in how people respond to them. And then once we've estimated that, say, based on empirical data, then we think about going out into the future when we are expecting different realizations of, say, weather shocks. What are the implications of, say, if we were on the blue line going to the pink. And so that's hypothetical, but there's actually a bunch of literature out there that does this empirically. And so you're seeing here 16 graphs all showing a relationship between, on the x-axis, some weather or climate outcome, and on the y-axis, some social outcomes. So A and B are actually, I'm just going to zoom into a few of these because there's too much here for you to adjust. But oftentimes, I just want to point out that you see often these nonlinear relationships where, say, as it gets, this is electricity consumption, as it starts cold and gets warmer, we see electricity consumption go down, less use of, let's say, heat pumps. But as it gets very hot, it goes back up again. So you have these kind of U-shaped or upside down U-shaped relationships. Or sometimes you have these, maybe it's flat and then it's sharp after a certain threshold. And so I'm just zooming in on mortality. So this can vary by location. So this is mortality rates in response to daily temperature percentile in Italy. You see, again, reduction in mortality when cold days are less cold, and then a sharp increase in mortality when hot days are more hot. But of course, it might not always be a U-shaped relationship, such as in India. They don't have that many cold days, and so in India, it might be driven primarily by an upward relationship with hot days. So this is kind of a taste of how you can think about using empirical evidence to quantify the impact of climate outcomes on human outcomes like mortality. Similar outcome for electricity consumption, I already talked through. This is in the US. Of course, this relationship might look very different in a country that doesn't have widespread adoption of air conditioning, where you might not have this sharp increase on the right. Similar idea looking at maize yields in the US, again, relatively flat until you get above about 30 degrees C temperatures on an hourly basis. Then you see fairly substantial drops in maize yields. So you can think. So this is how you can think about quantifying the impacts on society. Finally, labor supply, again based in the U.S. See large drop, particularly in kinds of labor like outdoor construction that drop off at particularly high temperatures. So how can this kind of work be used to inform an updated estimate of the SEC? So this is the paper that we published in Nature in late 2022. We have 24 co-authors spanning a number of different disciplines: demography, econometricians, Bayesian statisticians, climate scientists, people who model sea level rise and ocean, ice sheets, macroeconomists, all over the map. So I recognize the team. Here's all the faces of those names that were just on the screen. So this was really an interdisciplinary, interinstitutional collaboration between us at Resources for the Future, joint with David Antoff's lab at UC Berkeley, but also with contributions from folks at Princeton, the US EPA, NYU, the Electric Power Research Institute, Davis, UC Washington, Rochester, Tech, and Harvard. So I want to recognize all of their contributions. So the idea is that you can think about estimating the SEC in what's often described as a modular fashion. So each of those folks that I just showed you have very different areas of expertise. Some people have expertise on this box, some people have expertise on this box, and so on in that box, on that box. And so the idea was that each discipline kind of focus on getting their domain right, such as people who project a population or GDP, whereas others who focus on quantifying climate impacts, like in this graphs I just showed you, can focus on that. And then we can put all the pieces together. And so it basically flows from left to right. We start with probabilistic projections of country by year population and GDP, as well as projections of probabilistic projections of greenhouse gas emissions, not just CO2, but also methane, nitrous oxide, and trace gases. Taking seriously that we're accounting for uncertainty in those projections in a quantitative probabilistic sense. And then those feed into, particularly the emissions projections, feed into a model of the climate system. That's a reduced complexity model called the finite amplitude impulse response climate model that has its own uncertainties in how the climate system reacts to emissions trajectories and a pulse of emissions. That's going to produce climatological outcomes like increase in global temperatures, increase in sea level rise, impacts on ocean acidification, which are then monetized in the damage functions using functions kind of like what I showed you previously. And then finally, you actually are going to run this whole modeling procedure twice. So once in kind of baseline mode, and then once with an additional pulse of CO2 emissions that we're trying to value. That's that marginal concept of additional pulse or incremental pulse of CO2 emissions. And that's going to produce a stream of marginal damages. So the damages from that additional pulse beyond the kind of baseline version of the model, which we need to discount to the present to get to the social cost of carbon estimate. So this is going to a little bit more detail, but nonetheless still stylized of each of those components. We have projections of country by year population trajectories, income GDP per capita trajectories, again, country by year, again, probabilistic, and then emission trajectories, again, probabilistic pathways, accounting for the potential correlation between the emissions and the income. So the idea conceptually is that you might think that if we're on the high end of the income range, so we're having fast economic growth, that might fuel more emissions. So we're on the higher end of the emissions range in the near term. But you might think that might also spark innovation, technological innovation, that could help us reduce emissions more into the future. And that's in fact exactly what we see based on the results of our combined work, that this is all based on a combination of econometric analysis, statistical analysis based on historical data, supplemented with a structured expert elicitation process to account for the fact that we're probably unlikely to see the growth experience of the 20th century repeat itself again in the 21st, 22nd, and 23rd. As I already said, you feed this into the climate module, both with and without the pulse. That's the difference between the red and the blue area that produces changes in sea level rise and ocean acidification, which are then valued. And that difference between that red and the blue areas in the third column top panel produce a stream of marginal damages that we discount over time and then sum to get an expected value. But again, importantly, all of these lines are not just lines, but they have shaded areas representing explicit representations, quantitative representations of uncertainty based on a combination of uncertainty from all of the papers that we drew from, including the econometric uncertainty, the uncertainty from the expert elicitation, uncertainty in our understanding of how changes in emissions affect climate, and uncertainty in how changes in climate affect damages, and an uncertainty about the future path of discount rates. And that gives you this, not just a number, but a certain uncertainty ranges, or in this case, histograms of the SCC, which we then take the mean of to get our central estimate. So what do these look like? So here's the global population. I want you to just look at the solid line, the solid brown line, and then the gray area ranges. And so this is our global population projections. Again, this is done at the country by year level, but I'm just showing you global aggregates where we see slowdown of population growth, plateauing after 2100 before declining in the median case, but with substantial uncertainty between essentially lower population than today on the very low end to much larger population out into the future. On the emissions side, we see a perhaps overly ambitious expected reduction in greenhouse gas emissions, with emissions peaking in the relatively near term, but again, with a wide uncertainty range where it could be the case on the high end where emissions don't peak until after 2100. If you're comparing in both cases to the other colored lines, the dashed lines, these are the what are called the shared socioeconomic pathways. These are the pathways used by the IPCC, the Intergovernmental Panel on Climate Change. And you can see that our uncertainty ranges on population tend to be a bit wider, but we are we are kind of spanning the range of emissions pathways from the SSPs, with the exception of the very high-end SSP, the one where emissions exceed 100 gigatons per year of CO2 emissions compared to about 40 today, which a lot of people have, I think, rightly criticized as being kind of like a doomsday scenario that we're very unlikely to hit. And indeed, we are very unlikely to hit that in our projections. At the our very high end corresponds more to the medium high, well, high-ish, but not incredibly high case of the SSP 3 RCP 7.0. But it's the RCP, the 8.5 case that has been heavily criticized, and I think with good reason. This is just feeding those emissions trajectories through the climate model for projected increases in the CO2 concentration in the atmosphere. Again, with high uncertainty range, this is convolving not just the uncertainty in the emissions pathways, but also the uncertainty in our climate modeling, our understanding about how the climate responds to changes in emissions trajectories. And then similarly, that's ppm, atmospheric concentration. This is global temperature. Our central case is somewhere in the ballpark of about 2 degrees by 2100, and then rising, but at a lower rate after that, in the central case hitting around 3C by 2300. This is a bit lower in the median case than a lot of other projections because our emissions trajectories are fairly ambitious, but again, with wide uncertainty ranges in the extreme cases. The damage function. So I talked previously about how you can look to historically estimated damage functions that relate impacts of on, say, human mortality at future higher temperatures. And so we've built in 4 damage functions drawing from the literature. And each of these is showing on the x-axis the degree C of global temperature rise. And on the y-axis is damages, total damages, as a percent of GDP at that level, as well as uncertainty ranges. And so if again, as I said, we're kind of generally in the 2 to 3 C range, so we're kind of around here. So for mortality, which is the biggest component, we have total damages in the ballpark of 2% of GDP. This is the converting the change in temperature to expected changes in human mortality rates, valued at that value of risk reduction or value of a statistical life that we talked about earlier. So about 2% for mortality. For ag, there's some probability of benefits. This has to do with CO2 fertilization, but the median case is nonetheless damages. These are a bit smaller in the ballpark of maybe 1 to 2% of GDP. And then I want to show you, just highlight the last two, energy impacts and coastal impacts from sea level rise. The scale here is very different than the scale here. This y-axis goes 5, 10, 15. This goes 0.2, 0.4, 0.6. And so these are just much, much smaller. And so the biggest impacts that we're finding are coming from mortality and impacts on agricultural yields. Why is that the case? So this result is actually very consistent with the original studies that we drew from. And the answer is as follows. On the energy side, we see offsetting impacts from reduced heating expenses in cold countries. So think Canada, offset by increased cooling expenses in hot countries. And it just so happens to be the case that those two kind of tend to be a similar order of magnitude, and the net is still damages, but it's more muted. Of course, the distribution, this is the net across countries, so adding the positive and the negative, and so the distribution is also worth thinking about. But from a cost-benefit analysis standpoint, we tend to net impacts across members of society. And then lastly, we have a model of coastal responses and impacts from sea level rise. This is also a very small impact. It's the smallest impact in our model, less than 0.2% of global GDP. And a major reason for that is the model that we're using explicitly allows essentially coastal managers to adapt optimally with perfect foresight. They basically see what sea level rise is going to be, and they either retreat in advance or they build protection. And in the original paper by Delavan Diaz, upon which this model is based, she found that optimal adaptation versus suboptimal adaptation can reduce the impacts of the coastal impacts from sea level rise by something like an order of magnitude. So I think something like a factor of 10. So that's a difference between, say, 1.5% versus 0.15% for this category. So it may be surprising to some of you that, okay, if you add up the total damages in the ballpark of 2 to the degree C, you get maybe 2% from mortality, maybe 1 and 1.5% from ag, and basically close to 0, maybe 0.1, 0.2% from the other categories combined. And so we're talking about global damages as a percent of GDP of less than 3.5% from climate change. Turns out that that's actually a really big number if you put it in dollar terms, like dollar per ton term. And even if you do this by a back of the envelope calculation, you get the exact same conclusion. I think it's interesting. So the bottom line is I want to convey is that large dollar per ton values are not inconsistent with damages, gross damages that are just a few percent of GDP. Even though they might seem intuitively consistent, they're not at all. Just as another point of reference, I don't remember the exact number, but I think COVID reduced global GDP by a few percent, like maybe 4%. So this is a similar order of magnitude impact every year. So maybe that makes it seem like a bigger deal.
What is the climate damages versus
that's
that number?
I don't have it off the top of my head, but it's knowable. But yeah. Actually that kind of highlights the point. So it is going to be, our median is higher, substantially higher, because our I don't have it. I don't have the graph, but our central global GDP per capita growth rate is somewhere between 1.5% to 2% over that time period. And so you could do the calculations. So, but the point is that, you know, if you think about something growing at 2%, it gets really large. And then if you take 3% off of something that's enormous, that's actually a lot of dollars. Yeah. This is actually the same point from my previous slide. It's just when you add it up, you get something that's you know, under 5%. Although at much higher temperatures, you have a bigger spread in that. But in most of our modeling, we're actually living in this space here where we generally have under 5 and almost always under 10% impacts as a percent of GDP. This is pretty technical. So I use this very simple constant discount rate in walking through the previous how discounting works. We actually are using a discount rate that varies over time. And with the uncertain rate of economic growth, this is based on standard welfare economics dating back to Frank Ramsey's 1928 paper called A Mathematical Theory of Saving. Basically, the idea is there's a lot going on in this graph, but I just want to make the point that the discount rate itself, while it's centered, we use a discount rate centered at 2%, consistent with the circular A4 guidance, as well as a lot of the consensus in the recent macro finance literature. It actually varies. And the idea is that if in a future world that is richer and perhaps better able to withstand climate impacts, we might think about discounting more in that world. So basically, the short version is if we're in a part of our uncertainty analysis with a very wealthy future, then we're going to discount impacts to that future more. Whereas if we're in a kind of bad case scenario where things are going poorly, then we're going to discount that rate less. But in the central case, at least in the near term, we're using a 2% discount rate. So we're kind of symmetric around that. This is technical, so I'm not going to go into more detail, but if people want to talk afterwards, I'm happy to. The bottom line of this is that we generate 4 distributions. And so this is running our model 10,000 times, each time sampling all the uncertain components of the model, the uncertain trajectories of population and GDP growth, uncertainty in the emissions pathway, uncertainty in the climate model, uncertainty in the impacts of climate change, and that uncertain discount rate. And so I told you we're focusing on the 2% rate. So just look at the red line for the moment, and we take those 10,000 distributions. 10,000 SCC calculations. And the distribution of those 10,000 is that red line, and the central value, that expected value, the mean SCC estimate is $185 at a 2% discount rate. I already told you that the SCC, because it's such a long run metric, is going to be sensitive to the discount rate. So the SCC at 3 other discount rates, including the previous recommended value from circular A4, that gets you numbers down to $80 per ton of CO2 in the blue line. And then, if you go up and down 0.5% from the central case of 2%, obviously it can be higher and lower, but the central case is still that 185 estimate. The orange line is our central value, so that's still 185. We actually wanted to say, well, what if you threw out all of our work on understanding the mortality impacts, understanding the ag impacts, the impacts on coastal infrastructure, and the impacts on energy expenditures, and instead you used Bill Nordhaus's module that converts changes in temperature into changes in GDP loss. That's the blue line, so it's a bit lower, 152. Use the work by Peter Howard and Thomas Sterner, published in 2017, to update that component. It's a little bit higher, 205, but roughly speaking, it's not that sensitive. So you getting kind of a consensus across the numbers across when you vary which source of climate impacts damages literature you pull on. So I just wanted to show, this is from our paper as well. This kind of shows step by step. I talked about a lot of changes. And so which changes contribute the most to the updated number? So if we take the $44, which is from 2016, roughly consistent with the $50 from the old modeling approach, And we're going to update basically 3 of the 5 components that we did. So we updated the climate model to the new climate model. That's just more state of the science. We update the socioeconomics, so those trajectories of population and GDP, and we update that to account for that variable discounting, which is much more in line with economic theory. And the SEC goes up, but not that much. It goes from 44 to 59, so a $15 increase. So about a third increase from those 3 changes. Just update the damage functions. So we swap out the Bill Nordhaus's damage function with our 4 categories: effective mortality, agriculture, energy, and coastal impacts. Goes up by about another third, from about 60 to about 80, so about another $20 increase. And then we've updated the discount rate. We updated the discount rate. We go from the 3% discount rate down to the 2% discount rate, reflecting recent declines in real market interest rates. That's doing most of the work here. That increases it from this $80 to the $185. So if you were to, kind of break down these 3 buckets of changes, then about a quarter is due to the climate model, the socioeconomics, the discounting, and the damage functions, and about 3/4 is due to the updated discount rate. Again, this is perhaps unsurprising given the previous discussion about the discount. Sure. Yeah, that's a great question. So this is all global. If you were to take this number and get a domestic number, it's about a tenth as big. It's in the teens. I forgot the exact number, but it's like ballpark 15 to ballpark 15. So it's maybe a little bit less than 10%. Yeah. Yeah, that's right. Yeah. So yeah, the 2 big themes: discounting and standing. Who counts? I know there's interest in the social cost of methane as well, not just the social cost of carbon, particularly here in Louisiana. I wanted to point out an additional update from, this is just from our model, not strictly speaking EPA's numbers. I'll show you that in a minute. I want to show you the change in social cost of carbon versus the change in the social cost of methane. I've also got nitrous oxide as well, if that's of interest. So this is the results I just showed you for 2% and 3%. But I'm also showing you the social cost of methane. And what you can see here is our updated estimate is $1,900 a ton for the social cost of methane. But at a 3% discount, if we retain the 3%, the old social cost of carbon, as I've already mentioned, sorry, social cost of methane at a 3% discount rate was $1,500. So this is actually due to the updated climate science, which suggests that that methane breaks down faster in the atmosphere than the previous models suggested. And so that actually reduces the social cost of methane. And so the reason it went up from $1,500 to $1,900 is because of this lower discount rate. But again, methane is a short-lived gas, and so it's obviously much less sensitive to the discount rate, comparing this to this, than the social cost of carbon dioxide is, or the social cost of nitrous oxide, which is also a long-lived gas. And this is, comparing to what I already said, the 1,500 at a 3%. And if we actually properly compared it to the old estimates, but we had updated to a 2% discount rate, our social cost of methane has actually gone down substantially. This is just saying the same thing. Increases across the board for CO2 and 2O, but actually conditional on discount rate, it's actually, the social cost of methane has actually gone down from our model. So this is the analogous table from the EPA update. The only difference between what I showed you on the previous slide and what I'm showing you here is that EPA has basically taken our model and averaged it with the 2 other models. The one from the Climate Impact Lab called DSIM, and then the source of the damage function from the Howard and Sterner paper. And all 3 models produced pretty similar results on social cost of CO2, but there was a little bit more divergence. And so while our number went up to 1,900, once the EPA averaged it with the other 2 sources, the net change was only 1,600. So if those of you who may be using the $1,500 social cost of methane, the updated number from EPA is only 1,600, so not nearly as big of a change than the social cost of carbon change, again, due to the updated climate module and the fact that methane is much less sensitive to the discount. So that was our paper, but hot off the presses is a new paper by Lint Barrage and Bill Nordhaus. So, Bill Nordhaus won his Nobel in large part for his work on this. He's been working on his dice model since the 80s, I think. The last time he did an update to his model was in 2017. And so this was just published a few weeks ago, mid to late March, with Lint Barrage, is a very timely update. And it's based on completely different methods. There's no source of input data that is the same from our paper versus his paper. So I think it's an interesting comparison. So this is the 2024 paper. So the DICE model is short for the Dynamic Integrated the Dynamic Integrated Climate and Economy model. It goes back to the 80s, and it is widely used largely because it's very simple, and so it's easy to teach and for people to run. The key difference between our model and the DICE model are these four things. So one is that the DICE model has just one region, the world economy. Our model has 184 countries. So he has less spatial granularity. He doesn't have any uncertainty in the model. We take uncertainty very seriously, sampling many, many variables across 10,000 Monte Carlo draws. He uses a higher discount rate of 4.5% instead of 2%, although he does sensitivity analyses. And the trade-off is that by giving up on the granularity and the uncertainty, is that he is able to use the model in kind of what's called optimization mode. So we can say, what is the globally optimal emissions pathway that maximizes net benefit, so the benefit minus cost scenario, and they can run it under other very different setups. And so that's what he does. So just very briefly, these are the results on his pathways of CO2 emissions. So the orange line is essentially business as usual, rise in emissions beyond 60 gigatons from about today's 40-something to beyond 60 gigatons by 2070. The dashed orange line is, well, what if we extend the Paris Agreement with essentially no further, more ambitious promises beyond what has already been promised? And then he does a cost-benefit optimal case, which sees a drop and then a roughly flat line CO2 emissions trajectory. And then he says, essentially, green is like, what do we need to do to stay below 2 degrees C? And then lastly, the blue and the red are, what if he uses a different discount rate, not the 4.5% discount rate, but the 2% discount rate is consistent with our model. And so in that case, the blue line here is saying is kind of like the blue line up here. The light blue line is like the dark blue line, but the only difference is what's optimal if we use the lower discount rate. And you see going from a 4.5% discount rate down to a 2% discount rate motivates very different net benefit maximizing pathway of emissions trajectories. None of these get to net zero by 2050. The result on the right is just what happens when you take these emission trajectories and run them through the same climate model that we're using, the FAIR model. And again, you see rising temperatures mostly exceeding 2 degrees C, in the kind of business as usual case, exceeding 3.5 degrees. But generally speaking, the kind of net benefit optimal cases tend to have emissions trajectories that are, he changed the colors on me. The light blue on this graph is the dark blue in this graph and vice versa. So the net benefit optimal under the 4.5% discount rate exceeds 2.5 degrees. The net benefit optimal under the 2% discount rate is actually very close to mimicking the 2-degree ceiling scenario. The 2% can mean half a degree, roughly speaking. This is kind of another way of saying it. In the cost-benefit optimal case with the 4.5% discount rate, we see 2050 emissions that are about 40% below business as usual, and 84% reduction by the end of the century. This, compared to the baseline scenario, this creates $120 trillion worth of net benefits. It's benefits less at less mitigation costs. The 2-degree limit scenario achieves less net benefits because this one is obviously going to be better because it's optimal by definition, but it's pretty similar. So 107 versus 120 trillion in net benefits between those two. And then lastly, these are his updated, I should say there, because Lint Barrage is also a lead author. This is their updated social cost of carbon estimates based on their 4.5% discount rate. They have an updated SEC of $50. This should be notable because the previous SEC of $50 was based on a lower discount rate. And so this implies higher damages than the old numbers. And then they do these alternatives where they use other discount rates at a 3% discount rate, $87, at a 2% discount rate, $176. Very, very similar to our 185 conditional on using the same discount rate, but everything else in the model is completely independently sourced. So that's, I find this fascinating. This graph on the right is essentially showing the social cost of carbon on the y-axis as a function of that discount rate. So here's their baseline at 4.5%. And then here are that's that dot right here. And then the EPA numbers at the various discount rates EPA used. And so interestingly, the green line, which is the updated DICE model, conditional on a given discount rate, looks actually very similar to the EPA's recent update. And so again, discount rate matters a lot here. Oh, I already did. So I think this is good for time, so leave time for discussion. So I'll just kind of sum up and repeat some of the core takeaways. So the social cost of carbon is an estimate in dollars of the damages to society from an incremental ton of CO2. It has long-standing roots in economic theory. The recent update is a big deal. There's $190 per ton of CO2, which is a more than fourfold increase from the interim estimate. We're seeing increasing consensus conditional on the discount rate about the appropriate ranges for these numbers. But of course, the discount rate and the standing issue are key sensitivities here. So I'll stop there. Thanks.
Thanks, Brian. So I'll take the first question, then we'll pass it on. So I'm curious. So you looked at interest rates, and that was the main justification for the 2% versus the 3 or 4 before.
Yeah.
So I was at the Federal Reserve last week, and there was a lot of discussion of, has the neutral rate of interest shifted up in a post-pandemic world, et cetera? Did we have this 10, 20-year period of historically low interest rates, and now they've just permanently shifted up? So can you talk about that, the importance of that? How often should we update this discount rate? If we do it all the time, policies would just swing wildly. What are the trade-offs there that you see?
So my first reaction is that the nominal interest rate has gone up quite a bit in the past year. So is inflation. What matters is the real interest rate. And so right now we have a nominal interest rate of 5 to 5.5%, and we have inflation in the ballpark of 3%. We're still pretty much in that 2-point-something% ballpark. But I wouldn't in general, and this was a topic of debate during the Circular A4 update, which is, should you update your discount rate every time there's a non-trivial movement in market interest rates? And I think the original motivation by the 2003 calculation to take that 30-year average of real returns was, I think with good reason, justified by that we don't want to be updating it just due to transitory spikes or dips in interest rates. We want to have a stable basis for doing cost-benefit analysis. And so that kind of 30-year average seems to make sense. But and so if we did that with past year, I don't think it would change the conclusion very much. Yes.
Other questions? Because people online business so that they can hear.
Thank you. Just a couple of questions. One is follow up on Greg's question. So does the discount rate usually follow directionally with the interest rates? So as interest rates go up, the discount rate goes up and vice versa?
Can you elaborate? You mean in
sure.
In markets, is that what you're saying, or
No,
in the modeling?
So your discount rate is dropping from 3% to 2%, which increases the cost.
Mhm.
But interest rates are going up, not down. So do they typically follow in the same direction in terms of discount rates in general and interest rates?
So we look to interest rates as our benchmark for discount rates. A discount rate is the number you use in your analysis. A discount rate is, to the extent it's observed in markets, is observed as interest rates. So in that sense, they are one and the same thing. But as I said in response to Greg's question, we're still kind of in the 2% real return era. And even if we saw, so if we had the same conversation 2 years ago, real returns were 1% or something like that. And I wouldn't have wanted to base on that basis say, oh, we should be using a 1% discount rate. I think we should have something that's stable based on long-term averages rather than errant moves.
Okay.
Yeah.
Is there still a debate between scholars in terms of whether the discount should be reduced to 2% versus staying at 3%? Is that still part of the debate?
I think that there is a pretty strong consensus in the macrofinance literature that the real rate of interest over the past several decades has declined, and there's a real centering on about a 2% estimate from a number of different sources, both U.S. and foreign. And so I think there's a pretty strong consensus on that. I will caveat to say that the discount rate, the 2% discount rate upon which there is pretty good consensus, is the rate to discount consumption, which is how we measure damages and consumption, which means impacts on consumers. If a policy affects displaced capital, then you need to account for that as well. And I've written a paper with my colleagues Billy Pizer and Richard Newell on how you would go about doing that to account for capital displacement.
Okay.
Yeah.
One more question. The other primary driver sounded like it was the locational, domestic versus, global. So what's the scholarly views on that in terms of should we be looking at that from a more U.S. approach versus global? Is there a debate, and what are the two sides of that debate?
Yeah. So I would say there is a healthy debate on this question. If you're thinking about climate as a global externality, then it would be a very bad outcome if everyone just considered their own domestic impacts, because then essentially it's a race to the bottom. Of course, there are views that the U.S. should focus on the U.S. and what happens outside of our borders is not our concern. I think I have very strong moral qualms with that. But then setting that aside, there's a question about if you are going to consider only domestic costs of climate change, then you should also consider only the domestic costs of a regulation addressing it. And so to the extent that the costs fall on, say, a multinational company with foreign shareholders, then you can't count all of those costs as impacts on the U.S. So I think there needs to be like a matching between those two things. And if there's not, then you're effectively imposing a different kind of standing for one category of impacts than another, which is, I think, internally inconsistent.
Thank you. Great talk. Okay, so my question is about the agriculture production that you talked about. If I understand it right, you said with about a 2 degrees Celsius increase in temperature, you'd have about a 1% decrease in the percent in agriculture as a percent of GDP.
1%. It's not to get technical, but it's equivalent variation loss as a percent of global GDP.
Say it again.
Equivalent variation loss. So it's essentially dollars lost to society as a whole. Okay. It's not a change in, I mean, it is related to a change in the size of the ag economy, but it's technically speaking not exactly the same.
Gotcha. Okay. So I just looked it up.
Yeah.
And right now, GDP or agriculture as a share of GDP is 4.3%. Okay. So
in the US?
No, globally.
Globally.
Oh. So am I correct in saying if you lost about 1% of whatever you just said, you would lose about 1% of
percentage point.
percentage point. So agriculture would go from 4.3% to 3.3% or something like that.
That stands to reason. I would want to double check exactly how it's
Sure.
in our
Just
model, but yeah.
Rough numbers.
Yeah.
Okay. So that would be something on the order of a 25% decrease
Mhm.
in food production. So would that then feed back and cause mortality, which would change the social cost of carbon? Or could you model that, I suppose?
That's a great question. So we don't include that effect. This is purely essentially the monetized value of lost yields and higher food prices for consumers of food globally. It does not account for any mortality impacts. I don't know of any study that could get at that relationship, that could quantify that relationship, like how a change in ag yields would affect mortality, but I would love to talk about it if you have an idea. Oh, is that a question? Well, so I should be clear, it's 25% relative to baseline. Since the baseline's going up, then. But also the 4% might also not be 4% in the future, right?
Thank you. Also, great talk.
Thanks.
Follow-up question on the ag model. How much intensive margin change did you consider in terms of land use change and the like, given that we're going to have variation in temperature and we're going to have sort of a distribution of temperatures where,
Yeah.
certain land may come online that is not particularly well used now?
Yeah.
Thank
So I'm not an expert on the ag side of things. That's my co-author, Fran Moore and others. The ag damages were based on Moore et al., Fran Moore's paper in 2017, and I think it was Nature Communications. Basically what they did is they did a meta-analysis of something like 1,000 estimates of agricultural impacts, impacts of temperature and CO2 fertilization on ag yields for 4 major staple crops. And then they produced essentially damage curves for 16 global regions based on the regions in the fund model that are essentially nonlinear relationships between, on the x-axis, degree temperature rise, and on the y-axis, change in ag yields. And for each of these 4 crops. It's change in equivalent variation, so dollars lost due to changes in ag yields. Some countries saw increases in yields. These are cold countries that are primarily, increased land area and so, that's benefit, and also the CO2 fertilization. Other countries had negative impacts. So there's regional variations. Some countries benefit. There's also terms of trade effect, which is exporters. If prices go up, that's a good thing for their exports. So it accounts for all of those things. In terms of the question about change in land use and embedded in those estimates and adaptation, they were in there, but they're included as part of the meta-analysis. Other than that, I would have to refer you to my co-author, Fran Moore, for more detail. Yeah, sure.
The slide that you attributed to Michael Greenstone was very appealing, and it had the actual costs of various energy sources, and then you added the cost of carbon. So natural gas was the cheapest by far, and you look at that and said, well, renewables have a hard time competing with natural gas because it's so cheap. Then you add the cost of carbon, the social cost of carbon to it, and it now exceeds renewables, which should create an incentive to do those. But as I look at the reason that the cost of natural gas is so low is because of free market forces. Right? And so is there a way to get the natural gas price to what it theoretically should be to cover the social cost of carbon and keep it in a free market?
Yeah. So I see carbon pricing as the ultimate free market solution to climate change. You're basically taking a cost that is a real cost to society, but the market doesn't care about because they don't have to. A carbon price would do exactly that. It would take that cost that is being externalized and internalize it. And so that there's, in some sense, a level playing field. between, and it should be applied not just to fossil fuels, but anything that produces carbon dioxide emissions or greenhouse gas emissions. And so if everyone is paying their full cost, then you let the market compete. That to me seems like a free market solution.
Does that require a regulated price structure? Is that?
A carbon price. Well, so there's two ways you could do a carbon price. One is just a tax, and then that's it. And then you let them compete on the after-tax basis. The other is you could do a cap and trade system, which is that's also a market-based solution where then the price is set by the price of the emissions allowance is set by the market, and it might not be end up being equal to the social cost of carbon. It might be something lower, presumably lower, because in every cap and trade system that exists in the world, the price is lower.
So gasoline is taxed to cover infrastructure costs, but it still fluctuates as a free.
Oh yeah, the price of gasoline would still fluctuate. The price of natural gas would still fluctuate. It would just be a fixed adder,
Just in
basically.
the way that we
Yeah.
tax gasoline to cover road costs.
Yeah.
We tax natural gas to cover social costs of
Yeah,
carbon
and
costs.
you would
It's
tax
still a free.
gasoline or upstream crude oil in response to the carbon intensity of the fuel. Yeah. Yeah.
We had a 2-hour seminar on that exact topic about 2 years ago, and it's on our website. So I'll send it to you. Yeah, this was literally the nuanced. Yeah. It was fascinating. Yeah, right. Yeah, sure.
So when you talked about the impact on GDP and the 3 or 4%, I think you're talking about, is that the effect from imposing the tax? Talk me through that some more.
That's a great question. So no, that's the cost to society. That's the externalized cost of climate change on as a percent of GDP. Yeah, the cost to society of a regulation would be kind of the flip side of that. It's when everything I described was the benefits column of the cost benefit analysis. So what you're talking about is the cost side to which we're comparing it. And that, of course, is going to depend heavily on exactly what kind of policy we do. If we do a market-based policy like a carbon price, then economics says that that will be the cheapest, most cost-effective way of achieving a given target. You do it through, demand control regulations, obviously can be much more expensive.
The impact on the economy? Do we know the impact on the economy from the modeling done so far in terms of what happens if you do impose the tax?
So our model is a model of the impacts of climate change. You would have to look to different models to get an estimate of the mitigation costs, so the cost of reducing emissions. The last paper I talked about, the Nordhaus paper has both costs and benefits in it. And this model explicitly does compares the cost to the benefits and finds the policy trajectory that has the largest net benefits of mitigation minus cost of mitigation. And under his their 4.5% discount rate, that leads to this pathway of mitigation. We cut 40% of global emissions by 2050 and 80% by 2100. And then that's the solid blue line. If we use the 2% discount rate, then instead we're cutting much more aggressively. We're cutting down to this figure. That line seems inconsistent with the table. I have to think about that a little bit more. But anyway, the point being is that the model, the DICE model has the cost and the benefits side, but it doesn't have the same degree of granularity that we do have on the benefits. That's a trade-off. And there's other models out there on the cost side too.
Anything else? Oh, yep. Brian, yep. Stacey, yep.
Since you're here, might as well ask a question. Okay. So I think you started off talking about this is a common pool resource problem, common pool resource management issue. I happened to be teaching about Eleanor Ostrom yesterday, and you were talking just a minute ago about kind of this top-down cap and trade or market-based solution system. Ostrom obviously talked a lot about kind of bottom-up management of these commons issues. I was wondering if you had any thoughts on that? If we need sort of a top down and bottom up, or is top down good enough? What are your thoughts there?
So Ostrom's lessons are really great, but they're primarily lessons for small communities that, have strong social capital, trust, and the ability to, monitor each other and enforce, their decisions. That may be good at describing, small communities managing a fishery or something like that. I don't think it describes the UNFCCC or international negotiations between 200 countries over mutually agreed emissions reduction goals. And so I think it's hard to think about applying the Ostrom lessons to like Paris negotiations. That's my take here.
So you had that one slide where it showed all the like different potential impacts of or all the things that were accounted for in the model.
Yeah.
Right. And a lot of them were not yet accounted for. Correct?
Yeah.
And so my question is like what of those do you see as being developed in the near future? And how do you think that will change? Do you think like when and if some of those are further developed, it will change the output and the carbon price significantly in the near future?
The tough thing with this is that you don't know if something's big or large until you actually do the work. If we had known sea level rise was going to be 0.1% global GDP impact, it probably wouldn't have been worth the effort to include it. And so, yeah, the short answer is you don't know. But we, have an ongoing research agenda to account for certain things that are omitted. So as an example, our climate model is, great, state of the science, but it doesn't account for certain things like permafrost. Melting of the permafrost will release additional carbon and methane into the atmosphere, which creates a positive, meaning a bad feedback. That's not accounted for at all in our model. And so building in that component would affect the outcome. We have another project where we're working to account for biodiversity loss. How do you value that? And what's the impact of the loss of biodiversity in the Amazon, for example? That is a real value, but it's not accounted for in our model. So so we're working on it, but it's hard to know until you do the work.
Yeah.
Mm-hmm.
Is your work, your paper with all these other people, co-authors in Nature, replicable?
Yes.
If I and two other friends on one weekend want to replicate the whole thing.
Yes. Yep.
And because we are bored and we don't know what to do, and see
the
if
repo
we
is,
get the same thing that you do, or you did not make a mistake in your coding.
Exactly the same. The repository on GitHub is called MimiGive, MIMIGIVE. You can run it on, you can clone the repo on your local machine, run it. There's instructions. You can the code is also posted to Zenodo. The link is at the bottom of the Nature paper where you can download the code and run it. Soup to nuts. Everything will be in there. You'll get the same.
But that wouldn't be bored, Manfred. That would just be a fun weekend. I just want to be really clear here.
And it's written in Julia, by the way. Julia is a modern programming language that is pitched as the simplicity of Python with the speed of C. So something that would otherwise be, take many days of computational time to run these 10,000 runs takes less than a day. If you turn off the coastal impact, because we modeled more than 12,000 individual coastal segments, each one responding optimally, that takes a lot of computational time. It's so small, it doesn't matter to the SCC. You turn it off, it runs in an hour.
This was super informative. Thanks. So this is social cost of carbon dioxide. Out of curiosity, would you say the approaches are pretty similar for other greenhouse gases?
Yeah, so what I showed you is we also presented estimates of the social cost of methane and nitrous oxide, N2O. It revolves around, or entails the exact same approach. The only difference is instead of adding a pulse of CO2 emissions, you add a pulse of methane emissions, or you add a pulse of N2O emissions, and everything else is exactly the same. And so those are that's what I did to get the numbers that we showed you. In addition, the social cost of hydrofluorocarbons based on this model, our model, was recently published in Nature Climate Change by my colleagues Lisa Reynolds, Brian Partham, and Tammy Tan. So if you want all of those hydrofluorocarbons, of which I don't remember how many they did, but like, I don't know, a dozen or two, but you can get the social cost of hydrofluorocarbons from that. One thing I will say, don't use GWPs to convert from a social cost of carbon to social cost of methane, because the numbers I showed you had the social cost of methane was 10 times as large on a ton for ton basis as the social cost of carbon. The 100-year GWP of methane is 30. That would get you the wrong answer by a factor of 3. You would overvalue methane by a factor of 3 if you use the 100-year GWP. You'd over it by a factor of 8 if you use the 20-year GWP. So it's actually really important to value it using the gas itself rather than some CO2 equivalent. Yeah.
Oh, hi. First of all, great talk.
Thank you.
And I just wanted to say Eleanor Ostrom also won the Nobel Prize.
Yes.
Right? You know, to give that credit. But in terms of the work that she did, and especially at a more grassroots level and, you know, all kinds of stakeholder involvement, my question is, have you seen particularly good efforts to do the research translation or explain model findings, you know, to groups of like local decision makers that is particularly well done in your opinion?
We've so local decision makers, are you thinking like in the US or yeah. We've done some, so the Society for Benefit Cost Analysis recently held a 2-day webinar for anyone who wanted to listen in about going into much more detail. It was maybe 8 hours worth of webinar, going to much more detail on all these different components. I don't know how many local decision makers ended up tuning into that, but maybe we need better marketing or better dissemination. But states have shown interest. The state of New York has adopted a social cost of carbon of $120. This was before we published our paper. They believe 2% was the right discount rate. And so they took the old modeling underneath the $50, changed the discount rate from 3% to 2%, and the result was $120. So the state of New York has adopted that. A number of other states have expressed interest in adopting a social cost of carbon, and a number of public utility commissions have used it historically in part of resource planning and elsewhere. So there have been some steps, but it's, you know, it remains to be seen how much further interest there'll be.
Anything else? All right, well, so it's, you know, Friday afternoon, so you can go crack open your beer and run Brian's computer code and have a great weekend. So thanks so much, everyone, for coming, and thanks, Brian, for coming to Baton Rouge.